Well, good afternoon, everybody. Unless you're on the West Coast, Dr. Tyson Oxner has asked me to speak on the topic of fire danger rating systems and the potential for integration of soil moisture information into such systems. Before I begin, though, I'd like to talk about the organization of this presentation. I'd like to first talk about fire danger in general, what we mean by it, and also what we mean by fire danger rating systems, what they're designed to do and not to do. Then we'll look at 3 national fire danger rating systems that have been in existence for decades. Following that, we'll talk about the fire danger rating system we've developed here in the state of Oklahoma. After that, I'll talk a little bit about some soil moisture research that our OSU group has done relating to fire danger over the past 10 years. And then I'll conclude by talking about some research ideas that would aid the goal of integrating soil moisture information into fire danger rating systems. So what do we first mean by fire danger? A simple definition might be the ability or potential of a wildland fire to start, spread, resist control, and do damage. In other words, the higher the fire danger, the easier it is for a wildland fire to start and spread, resist control, and do damage. 3 of the major fire danger factors are fuels, weather, and topography. When we talk about fuels, we're talking about the type and amounts of fuels, their fuel moistures, whether they're live or dead. Weather is obviously very important, and topography as well. Some of the assumptions and limitations in fire danger rating. First of all, it's not meant to be used for fire behavior on a specific landscape, in other words, on a field-by-field basis. Within each fire danger rating area, in the case of our Oklahoma fire danger model, 500-meter square pixel, the fuels, weather, and topography are assumed homogeneous. And so what you get as a result of that with these ratings is the average fire danger over the rating area. Purposes of fire danger rating are several: provide public warnings, set preparedness levels, difficulty of fire suppression over a wide range of conditions, and helping fire managers make wise management decisions, both real time and in the future. When we talk about our fire danger rating system, we're actually talking about a system that integrates selected fire danger factors into one or more qualitative or numerical indices of fire danger. So let's first go to the country of Australia and talk about the Australian fire danger rating system. This has actually been in existence since the 1960s. They're currently, however, in the process of creating an entirely new fire danger rating system that will be more comprehensive and flexible, but I'll talk about the one that's currently in existence. It currently consists of 2 indices, each with 6 fire danger categories. The first index is called the MacArthur Forest Fire Danger Index. The second, the MacArthur Grassland Fire Danger Index. Let's first talk about the Forest Fire Danger Index. It was designed for a standard or representative eucalyptus forest, an example of which is in the photo in the background. Weather inputs include temperature, relative humidity, wind speed, rainfall. They also use a drought code, which is calculated either using KBDI or a soil dryness index. As we go through these systems, I want you to notice the lack of explicit soil moisture information, whether it be from an in-situ network or remotely sensed from satellites. The Grassland Fire Danger Index was designed for a standard representative grassland. Inputs include temperature, relative humidity, wind speed, and the degree of curing, which is typically observed using visual estimates to provide that information. Here are the 6 categories for both the forest and the grassland indices, and examples of some products from different states of Australia. Here's one for Victoria, showing the fire danger based on these indices for May 2, and also here's one for Queensland, which was actually a forecast for May 5. Let's now go to Canada and talk about the Canadian Forest Fire Danger Rating System. This has also been around for decades, since the 1970s. It consists of 2 major subsystems: the Forest Fire Weather Index System and the Forest Fire Behavior Prediction System. Let's first talk about the Forest Fire Weather Index System. This was designed for a standard representative jack pine forest, an example of which you can see in the background. It consists of 6 components. 3 are actually moisture codes for 3 different layers beneath the forest floor. And then it also calculates 3 fire danger indices, including the FFDI. The weather inputs include temperature, relative humidity, wind speed, and rainfall. Again, notice the lack of any specific soil moisture information. And here's an example of a national map of the FFDI that was produced for the April 30th. Forest Fire Behavior Prediction System has 16 fuel models, including a grass model. It incorporates 3 outputs from the FFDI system into its calculations. It utilizes topography and models foliar moisture using elevation, location, and date. So in other words, it's the same from year to year based on where you are, the elevation, and the day of the year. Weather inputs, in addition to those that were required for FFDI, include wind speed and direction. The inputs for fuel are only one if you have a grass model, and that would be the degree of curing, which again typically would be provided using visual estimates. And the outputs from this system are more the physical characteristics of the fire, so it'd be more in line with the National Fire Danger Rating System of the US, which we'll talk about shortly. And here's an example of a national map for head fire intensity. This would be similar to the burning index of NFDRS. So now let's go to the United States, talk about the National Fire Danger Rating System. This has been in existence since the original in 1972. There were major revisions in 1978 and 1988. And a new revision has been developed called NFDRS 2016. It's not yet operational to my knowledge, but will be very shortly. Matt Jolly is the main designer behind this, and any particular questions on this system you can address to him. There are 5 standard fuel models, reduced from 20 in each of the 1978 and 1988 versions of the NFDRS. But like in those systems, it continues to explicitly calculate live and dead fuel moisture, as well as the dynamic fuel load transfer between 1-hour dead and herbaceous fuels. However, in this system, the live fuel moisture and the dynamic fuel load transfer is calculated as a function of Jolly's growing season index, the GSI. It still uses KBDI as a drought surrogate to add extra dead fuel when KBDI is greater than 100. And the inputs are temperature, relative humidity, rainfall, wind speed, solar radiation, latitude, day of year, which are used to calculate photo period. Again, notice the lack of specific soil moisture information. The outputs are the same as in past systems, BI, ERC, SC, and IC. And the daily maps are created. Here's observed fire danger class on May 2, and here was the forecast for May 3rd. Now let's go to the state of Oklahoma and talk about our system, which we've developed. It all began basically with the implementation of the Oklahoma Mesonet in 1994. We currently have 120 stations, and we provide information every 5 minutes for the weather parameters. So here's an example of a fire weather map showing the amazing resolution we get in the state of Oklahoma because of this, this infrastructure that we have. Back in the mid-90s, mid to late 90s, Larry Bradshaw and Bob Bergen of the U.S. Forest Service saw a tremendous opportunity to implement the National Fire Danger Rating System on the first statewide automated weather station network. And so they worked with us and Mesonet to develop such a model. Later, we also worked with Ralph Nelson, who developed a dead fuel moisture model called the Nelson model, which we also use in OK Fire, and they also will be using in the NFDRS 2016. So a little bit about OK Fire. It utilizes the 120 station Oklahoma Mesonet for past and current conditions. It utilizes an 84-hour forecast from the NAMA model, the North American model, for the next 3+ days. Fire danger model is loosely based on the 1978-88 NFDRS, but uses different inputs and methodologies. It does have the same outputs, however. Weather inputs are temperature, relative humidity, rainfall, solar radiation, and wind speed. Again, notice the lack of any explicit soil moisture information. It uses daily satellite information from MODIS. We take 7-day composites of the 500-meter resolution NDVI and calculate a variable called relative grainness, which actually Bob Bergen was instrumental in developing that system. And we use the relative grainness to calculate live fuel moisture and the dynamic fuel load transfer. So basically in our system, relative grainness is the same as the GSI and the new NFDRS 2016. They both serve the same purposes, whereas we use satellite information for that. We have 9 fuel models in our current system. Again, 500-meter resolution. We use a standard fuel model map for our map products. We also retain KBDI as a drought surrogate to add extra dead fuel. And the fire danger model actually runs every 15 minutes. So it's very real-time type of information. And the outputs are available in map, chart, and table formats. So I want to show you some examples of the fire danger model from the Ray fire, which was a big fire in Northwest Oklahoma in April of 2018. The white triangle represents the location of the fire, and these are fire weather maps, weather parameters, which are actually updated every 5 minutes. So these maps are from 5 p.m. April 17th. So here's temperature, relative humidity, and winds. You can see there was a dry line located here. So the fire was really expanding and blowing up at that time because it was behind the dry line. Winds, directions, and speeds. 1 hour dead fuel moisture and 10-hour dead fuel moisture. These dead fuel moisture maps are updated every 15 minutes, as are the fire danger outputs, burning index, spread component, ignition component. So this is just some examples. You can see with the frequent updates how useful such information can be to fire managers who are actually fighting the fire in real time and looking into the future over the next 3 days as far as what's to happen. Now I want to talk a little bit about the soil moisture research that we've conducted over the past 10 years at OSU. This is part of our research team. There I am, Eric Kruger, who's currently online, I believe. Of course, Tyson Oxner and Dave Engel. We looked in particular at a variable called fractional available water, in particular in the 0 to 40 centimeter soil layer. Because Mesonet has soil moisture sensors, we have an ideal system to actually calculate soil moisture in Oklahoma. And this fractional available water typically goes from 0 to 1. If it's 1, that means the plant has all the available water, it's at field capacity. If it's at 0, that means it's currently at the wilting point, so the plant actually has no water to work with. And in particular, we looked at large wildfires over 1,000 acres from the time period 2000 to 2012. There were actually 501 of them. And we wanted to see the relationship of thaw to large wildfire activity as a function of either dormant season or growing season. And here's just a graph of fire size versus thaw over that 12, 13-year period. And you can see during the growing season, most of the large fires occur at a thaw value of 0.25 or lower. Actually, most of them occur at 0.2 or lower, whereas during the dormant season, the thaw values are scattered all over the place. So that shows, along with other research we did, that fire activity and fire size are closely related to thaw during the growing season. We also looked at the relationship of thaw to KBDI, which, as you've seen, is a common denominator in a lot of the current systems. We looked at actually the 10 largest fires of those 501 fires. Here's one of them, Chester 2009. You can see how the thaw in the 0 to 40 centimeter in the solid green line reaches the critical value actually about a month before the fire actually occurred, whereas KBDI in the solid brown did not even reach critical levels, which we typically consider 600 to 800 at all. So thaw gave certainly warning of the impending possibility of a big growing season fire where KBDI would not have at all. Here's another example, the Freedom Hill Fire 2012. Here the thaw value got to 0.25, actually 2 to 3 months ahead of the time of the big fire, whereas the KBDI only reached critical values of 600 about a month before the fire. So again, this shows that that FFDI provides much greater lead time. In fact, for the 10 largest growing season fires that we analyzed, the average lead time for before the fire was about 10 days. So it had a 10 days early warning compared to the KBDI system. So again, it's much more sensitive to what's actually going on in the soil and provides an earlier warning for possible fires than KBDI does. As a result of our research, we developed an operational product for Oklahoma, which was implemented in the fall of 2017. This is it's called 16% plant available soil moisture. We basically multiplied FFDI by 100 to put it in a percent scale. We note that it's for large wildfire potential during the months of May through October. So anytime FFDI is under 0.2 or 20%, you can see that these are the danger areas and so forth. Just to show you how FFDI and KBDI maps can differ, this is for the same day, July 11, 2019. The FFDI map was already showing a lot of areas that were in danger, these red areas and also in the orange, whereas the KBDI map was showing everything nice and green. It actually suggests no fire danger at all given appropriate fire weather conditions. So now I want to conclude by talking about some research ideas, how to integrate soil moisture to better assess and predict fire danger. I think there's two types of products that can result. One would be standalone tools using soil moisture information. An example of that would be the 16% plant available soil moisture map that we currently have in OK Fire. In other words, this is just a standalone tool that's not integrated into any existing fire danger rating system. The other type of product, of course, would be integration of soil moisture information into components of existing fire danger rating systems. So ideas for soil moisture research, and this would be using either in-situ networks or satellite remote sensing of soil moisture. And since satellites will definitely be used in the future, as will in-situ networks, it makes sense to compare what the in-situ network is measuring with respect to soil moisture, comparing with what the satellite is actually sensing. And I'm sure some of that research is already currently being done. Also, it would be useful to research the relationship of soil moisture to live fuel moisture and see if soil moisture could be used by itself to model live fuel moisture as a function of different fuel types and time of year. That currently is not being done. Also, the role of soil moisture in the dynamic transfer of fuel loads between 1 hour and live herbaceous and/or deciduous types of fuels. This also is not currently being done. And I believe Tyson is going to talk about these two topics and some of the research we have done in his talk later to come. Also, soil moisture as a replacement for some of the drought codes in the existing models and surrogates that use KBDI and other such drought indices. Why not use soil moisture itself as a component in some of these systems that's either directly measured or satellite remote sensed? And then the final suggestion, the investigation of antecedent soil moisture as a factor in increased or decreased fire danger. In other words, if we have higher soil moisture in the growing season, that most likely will result in more fuel for burning in the dormant season. So we can investigate lag times in the past, the effect of soil moisture on current fire danger and so forth. So with that, I'd like to conclude and thank you for the opportunity again for presenting. And at this time, we'll open it up for discussion and questions.